Okay, so we are looking at linear regression, scatter plots, things like that. So there's a little bit of vocab to go with this. So you can write electronically or you can write on paper, right? A scatter plot is a graph of the relationship between two quantitative variables. It's really important. Yes, ma'am? Okay, sure. Remember, it's quantitative, not qualitative. So we need numbers that make sense. What's a quantitative variable? That means averaging it or performing mathematical operations make sense, right? Like your phone number is not quantitative. We can't add up all your phone numbers and find the average phone number. It doesn't make any sense, okay? Explanatory variable, right? Explains or causes changes to the response variable and is graphed on the x-axis. Now, what did you used to call this last year? What variable did you call this? Dependent, right? Oops, independent, sorry. I went to Y. Independent, and then of course, so you could think about this as the independent variable. It's explaining or causing change to the other variable. So when you use this in science all the time, figuring out which one is the one that you're plugging numbers in for, right? Usually if time is one of the things, time goes on the x-axis, right? If you were driving to Austin, time would explain how far you are, right? Okay, response variable measures an outcome. Right? Or a result. And is graphed on the y-axis, which is the dependent, which you think of as dependent. Okay, so in algebra, you call it independent. In stats, we call it explanatory. In algebra, you called it dependent. In stats, we call it the response variable. So a little bit of variation on what you did before. I put explore here. Sometimes we just explore a relationship and we don't really have an explanatory. So sometimes we just explore, right? A relationship. Right? We may not have explanatory or response variable. Right? Does that make sense? Not everything causes something else. Not everything is explaining something, right? Okay. Some words that we're going to use to describe things. We have trends, shapes, directions, forms, and strengths. Right? So a trend is kind of what's going on, right? What's the trend right now? So for us, we either have a positive or a negative association, possibly none, right? If it's positive association, then the scatter plot slopes upward. If it's negative association, downward. Now you used to just say it has a negative slope last year when you were a little kid, right? Or 2 years ago in algebra, you'd say, oh, that has a negative slope. We're fancy now and we'd say that's a negative association, right? We're using big words so we can make fancy sentences. We're saying the same thing, aren't we? Okay, so that would be like this, And this would be like, right, going down. The shape, we want to know if it's positive or negative, or neither. Why did I try to write neighbor? If I graph the amount of time you studied and your grades, that would have a positive association, right? If I graph the number of hours you watch TV and your grades, most likely that would be negative. But if I graphed what kind of dog you have in your grades, would there be any relationship? No. Your dog, whether you have a Chihuahua or a Labrador, is not going to change your grades. So sometimes there is no relationship. Of course, type of dog would be categorical. So is it straight or is it curved? We're specifically looking at linear regression. So we're looking for linear relationships, but we have to identify if some stuff is curved. What's going on right now in our world that's a curved relationship? Cases of what? COVID, right? Germs do not have a linear relationship. You don't have 1 to 1, 2, then there's 2. You know that they're exponential, so that's a curve heading up, right? Direction, are all the points headed in the same direction? Form, what does it look like? Are the points close together in clusters? Or are they scattered? Right? If you saw this relationship, that makes sense, right? You would say, if I gave you this, you'd say, oh yeah, that's going up. But if I gave you this, are these variables related? No, that looks like it's snowing out, right? If your graph looks like snow, that's not, we don't have a relationship. Maybe if I checked your shoe size and your grades, has nothing, right? A size 7 shoe does not guarantee you an 8. Strength is determined by how closely the points follow a clear form. This would be very strong, right? You could definitely tell they're going up. So if your points are closer together, you have a stronger relationship between your variables. Okay, an outlier is an individual value that falls where? Inside or outside? Outside. Outside the overall pattern, it is an important deviation. And I want to put a note here. Greatly affects R value. Okay, it can really pull your R value out of whack. And we'll talk about what an R value is in a minute. Okay, 2 big words here. I'm sure you know. What's the difference between interpolate and extrapolate? If I said you're going to plug 2, 4, 6, 8, 10, those are the values I gave you, 2 is 1, 4 is 8 or whatever. If I gave you 2, 4, 6, 8, and 10, and then gave you the Y value for those data points. So if I gave you 2, 4, 6, 8, 10, you could predict 7. It's in between 6 and 8, right? It's still within where you were looking. That's interpolating. Extrapolate means you want to go outside. So if I gave you 2, 4, 6, 8, 10, and 12, you're trying to predict 20. So you're going outside the data. So here you're figuring out within your data. Here you're going out. So predict a value of the dependent variable for an independent variable that's in the midst of our data, right? So if I gave you this 0, 2, 4, you could predict 3. right? Because 3 is still within there. Or here, extrapolate, I might try to predict, you know, 8. 8 is going past, but I'm looking at the trend of the future. Now, one of the things, this is outside the range of our data. This can be a really bad idea. We need to make sure data continues on forever. If you write an equation, a linear equation, does it go on forever? Yes. You can plug anything you want into it. In real life, do things continue on forever? No. If I took what you weighed at birth and I plotted, you know, by 6 months, you've doubled your weight. If I were to plot some of those and I quit, like if I just measured you from 0 to 3 and I kept a line going, how big would you be now? You'd be huge, right, on that line. So you always have to take context in what happened. How come you're not 12 feet tall? That's what my graph would say. Well, because we know we reach a maximum height, right? You stop growing. So it's always important when you're going to extrapolate to say, does this make sense? Can I really get that big? Because if I did a growth chart for you, the growth chart will never quit growing. You might really should be 15 feet tall by now, right? So you cannot always extrapolate. We must be careful with that. Now, sometimes it's a good idea, right? But we want to make sure that you don't come up with ridiculous answers. Like you measure your puppy's weight for the first 6 months, and you draw a graph and predict that by the time he's 2, he weighs 400 pounds, right? Puppies grow fast, right? Then they quit. Okay. Understanding correlation. What does correlation mean? What is correlation? Yeah, it's kind of like, well, I notice when she does this, she does that, right? One may not necessarily be causing the other, but you notice a correlation, right? Direction describes direction and strength of the straight line relationship. So direction, positive or negative, and strength. And you're going to see strength is between -1 and 1. So if your R value, and that's a value that's calculated, we can use our calculator. We don't have to do it by hand. If your R value is 1, that means it's exactly linear and every point is on the line. As the R value gets close to 0, then we don't have a good relationship, right? If your R value is 0.2, then more than likely this really isn't linear and you're doing the wrong kind of math. This math won't work for it. Does that make sense? The negative or positive doesn't make it stronger. That's just telling us if it's trending up or trending down, right? Okay. A couple of things. I just typed these. I didn't think you want to write them all. Correlation does not change if you change units of measurement. So if I did your running speed and how far you got, I would have an R value. If I change you from feet per second to miles per hour, your R value wouldn't change. It doesn't matter if we change unit, that strength stays there. Okay. You don't run faster or slower if I just convert it to feet instead of miles, right? You don't. Okay. So really important, correlation does not change when we change units of measure. So if you get a question that says, hey, what would happen to the R value if we changed it into miles per hour? You'd say nothing, right? Correlation ignores the distinction between explanatory and response. It's just a number, right? It's telling you how strong that relationship is. Correlation measures the strength of straight line associations. So that's why if your R value gets very small, like 0.1, that means your relationship wasn't linear. Not everything is linear, right? The correlation is strongly affected by a few outlying observations. So if you're looking at a graph and they want you to guess the R value, if you have an outlier that's far off, it's really going to pull that R value down. You're going to lose your strength. So you, the statistician, may have to say, wait a minute, I have one value outstanding. Let me pull that out, see how strong. Well, the rest of them are really strong, and figure out what happened with that one, right? You don't just write the number down and let it go. You guys have to think about it. R squared is the fraction of variation in the values that is explained by the least squares regression line. What? What that means is if you got an R squared that was 0.632, that means 63% of your observed variation, so 63% of the variation you see is explained and accounted for by that straight line variation. Does that make sense? Let's do some now. We've kind of just talked and looked at vocabulary words. Do vocabulary words make a lot of sense by themselves? They really don't. Yes, ma'am. So R value is 4. Yes, yes. And what R really helps us figure out is, are we linear? If R is close to 1, then we know we have a really strong linear relationship. If that decimal gets smaller, like 0.1, then I'm like, are you sure you should be looking at a linear relationship? I think maybe this isn't linear. That's just too weak, right? And maybe it's nothing. Not everything's related, right? So let's look at some example. And you notice that this says scatter plots. Bivariate data. What does that mean? What is bivariate? That's a new word for us. 2 variables. And I kind of want to look at, I'm going to look right here first. Okay. When you look at a scatter plot, algebra 2, you would have drawn it and put some numbers down and that's it. Statistics, you're going to explain what it means. So we always want to look at the direction, the form, and the strength. Right? Direction, positive or negative, right? The form, linear, curved, exponential, etc. We're really interested in linear right now. That's what our focus is. And then strength. Now, how do I describe strength? Here's a little guideline. There's not a hard cutoff where you could say, it hit that, okay. But if you look at this, and I know y'all can see it. There we go. So if I'm up here, right, like between 0.8 and 10, this is strong. If I go from like 0.5 to 0.8, I'm moderate. So let's look at that. And this is talking about the strength of R. So if I were 0.8, how would you describe a 0.8? Moderately strong, right? It's kind of in the middle. So here's moderate, here's strong. So if I'm in between, I'd say moderately strong, right? And there's not a hard cutoff. This is a little bit of a judgment call. Here we're saying there's a weak. If I got all the way up to 0.5, I'd say weak to moderate because I'm in the middle of weak and moderate, right? Does that make sense? And of course, the same thing on this side. They're the same numbers. They're just negative. It's just because it's trending down instead of trending up. But remember in statistics, we said we're going to BS. What does that mean? What does BS stand for in statistics? Be what? Be specific. So we don't want to say, oh, it's going up. We want to say, oh, it is trending up in a positive direction in a linear format with a weak to moderate strength. We want all those words in there. Can you look at this list if you take a test? Yeah, it's right there in your notes. We could even write it down on a brain if we want to, right? So weak, moderate, strong. So if I were right there, I would say moderate to strong. We don't have to say weak or moderate. We can say weak to moderate, right? If it's moving up, like if I were right in this area, I might say weak to moderate. Because you're the statistician and you're trying to explain to someone what's happening with these variables. What kind of relationship is going on? Why do we do that? Why do we care about the relationship between two numbers? Because it's our crystal ball. That's how we make predictions. We love predictions, right? How many of you check the weather at night before you get dressed, before you put your clothes out for the next day? Anybody check the weather? Because you're trying to predict what the weather's going to be like tomorrow, so you pick the right clothes. If it's going to be 94, most of us don't wear a sweater, right? If it's going to be 24, most of us don't wear tank tops. So we want to know what's predicted for the weather. A lot of things we want to know what's predicted. If you're going to have an event at school and you're going to serve treats, you know, whatever your cause is, maybe you have cupcakes. Do you want to know how many people are predicted to be there so you have the right amount? Yes, right? So we're constantly making predictions. So this is how we describe those predictions. Calculator steps are going to be on the next page. There's just not enough room here. Okay, so how are you going to describe strength? Strong, moderate, weak, weak to moderate, moderate to strong. Use your words. Direction, positive or negative, that's easy. And of course, form is easier. Is it linear or is it not? Right? Okay. I'm going to do these. I'm kind of going backwards, but I think it helps to look at these before we make our own. So let's look at these little pre-done pictures and see if you can describe the DFS. What's the DFS? Direction, form, and strength. So what's the direction here? Positive. What's the form? Does it look linear to you or curved? What would you call it? Strong or moderate to strong? Strong. This is a strong relationship. If you graph your points and it looks like this, you should be pretty safe to make some predictions of numbers you don't have, right? That's a good, this is linear. Whatever variables this person plugged in, they do trend up in a linear fashion. What about this guy? Direction? Positive, right? Form? Is it still linear? Still linear. But how would you describe the strength this time? Moderate to strong? It's a 0.75, which is really close to 0.8, which is in the middle, and 0.5. I'd kind of call it moderate to strong. When we describe these, is it a little bit gray? Is it black and white with hard lines? No, there's not every number written down and this is strong. It's a judgment call a little bit, right? What about this one? What's the direction? None. It looks like snow. If it looks like snow, this isn't linear, right? What's the form? None. What's the strength? None. You can't even call it weak. There's just none. R is 0. That tells you that whatever this person plugged in, they need to use some other math to figure this out. It's not linear. If I took a sine wave and plug the numbers in, it probably looks something like it's not going to work, right? It's just all over. That's a bad example. Never mind. Okay, what about this one? What direction? Well, it's negative then positive, right? So this is not linear, is it? It's curved. Is it a strong relationship? Are they tight together? Your dots are close, so it's strong, right? But it's not linear. That's why we don't have an R value. This R value probably be 0. It's not, it's linear, or it's curved, sorry, it's not linear. Okay, what about this one? Yeah, that's going down, and my R value is always going to be the same as my direction. 4, it's linear, right? Now, how would you describe it? Moderately, moderate to strong. It's in the middle of moderate and strong, right? And then what about this one? Negative. It's still linear. Strong, weak. What is this one? Yeah, this is, above 0.5 is kind of moderate, but this is weak to moderate, right? Or moderate to weak, whichever way you want to write that. Does that make sense? Is that good? Okay. So now we're going to plot a fake one just to talk about it. We're really bad as people about saying something causes something else, right? Like I could say watching TV causes your grades to go down. Is that true? They're related, but does the TV really what's causing your grades to go down? It's the lack of studying. So we got to be careful and make sure we're careful with cause and effect versus correlation. A lot of times there's a correlation. We really need to do experiments and things to have causation. So a lot of what you think causes, if you really think about it, it's really a relationship. It's a correlation, right? Tips for plotting the explanatory variable. Make sure that you label and scale. Oops. Now in math, you can't read my writing. In math, we usually label a graph 10 by 10. In a real world thing, do we want a 10 by 10 usually? No, if it's anything big, like even your grades, or I'm going to do one with how fast you drive, we need to label and scale appropriately so we can fit our dots on there, right? And your scale, remember, must be uniform. If you're counting by twos, you have to count by twos the whole way. You can't do a scale that says 0, 2, 7, 12, you know what I mean? Okay, so I'm just going to compare driving and age. Driving versus age. And I'll do male and female. So can I take a graph that's all quantitative? Can I color code it and get some qualitative information on there too? Like I can use the same graph for guys and girls if I just use different color dots. I could do teenagers versus adults. I could do anything I want, right? I can do different color dots. So let's say that this is driving speed. And this is age in years. Here's the title of my graph, although it's down here instead of up there because I don't have room. Okay, so if I take males, I'm just going to put nothing fancy. Right? And I take females. I made this up. I'm not going to go look for real numbers. I just want to talk about this scatter plot. So what would you say about this? Do you agree if I make the statement, people drive more slowly when they're older? Does age, do you agree? Do you think teenagers drive faster? I used to be one. I'm sure they do. Now, is it age that causes you to drive more slowly? It's not age. Why would I drive more slowly? Why do you think your parents drive more slowly than you do? They have what? More experience. How about wisdom? Right? How many of you have ever gotten speeding tickets? If anything will make you drive more slowly, it's getting speeding tickets. So maybe by the time you're 20, you've had a speeding ticket. They threatened to take away your license because you were going 147 down the boulevard at 2 in the morning. Right? What else? What happens on that beautiful day when you drive home from the hospital with your baby? Do you drive 100 miles an hour? No. See, your parents used to drive fast too before you were born. Then you were back there in a car seat, and then they're like this going, you know, scared half to death. So becoming a parent could be a reason you would slow down. Now, as I get older, would my reaction time slow down? As I like think your grandparents? What about your eyesight? Have y'all ever ridden with some older people? By older people, I mean your parents or grandparents, and they have trouble seeing at night? Why is that? Astigmatism, cataracts, there's all kinds of things. So is it their age that's making them slow down at night, or is it their eyesight? There's a correlation to age, because as you age, your eyesight declines, but it's really the eyesight itself that's the cause. Do you see what I'm saying? So be very careful with cause and effect versus correlation. There's a definite correlation in your age, but it's not actually the age that's causing it. It's all these other things. Can you think about it? Also, younger people, what do you feel? Younger people, according to psychology, invincible. You don't think you're going to get hurt. Once you have kids, it's all you worry about, right? So just all this is doing is pointing out the fact to you that you've got to look at correlation versus causation. If you watch too much TV and your grades go down, did the TV cause your grades to go down? No. Why did your grades go down? You weren't doing your homework and you weren't studying because you were watching TV. So, but there's a correlation because the TV was the reason you weren't doing your homework, right? Does that make sense? These are very, very, very hard, easy to mix up and start thinking, well, this causes that. Does it though? Right? All right, so let's do a problem together and then I'll let you work. One more thing I want you to notice about statistics versus algebra, and it's in your calculator both ways, so it's no big deal, right? Look at that sign, right? Look at the equation. What do you notice about the equation? In algebra, we wrote our equations like this. We like 3x plus 4. In stats, they like to do it this way and say 4 plus 3x. Doesn't matter, it's the same thing. But you can ask for it either way in the calculator. Is this number next to x still the slope? Is this still the slope? So in statistics, they like to call the slope b instead of m. No biggie, it's going to come out the same thing, but you just want to notice that, right? B is the y-intercept in algebra. In statistics, we like to call it a. But if I said 3x plus 4 or 4 plus 3x, you're not going to care whether they're a's or b's. You know that the slope is next to the x and the other number is the y-intercept, right? Just a little thing to confuse you. We like to change it in stats. Okay, so we're going to look at now, if you get some, you go out and collect some data, and you know we love to collect data, don't we? Especially M&Ms. We can write this LSRL, what is that? That is a least squares regression line, right? And it's a line that represents a linear relationship. Between two quantitative variables. Okay, it's quantitative. We're talking quantitative data here. And why do we need a least squares regression line? To make what? Predictions. This is all about predicting, right? We want to know everything. We want to know what the weather's going to be like tomorrow. We want to know what the weather's going to be like over Thanksgiving, and we get mad because it only goes 10 days out, right? True? All right. So let's look at how to put this in the calculator. It's very easy. You've done it before. So one of the first things, clear your calculator real quick so we can go through all the steps. So second plus 712. Let's put clear second plus 712. That's how you clean your calculator. Okay, so the first thing we're going to do is go to mode and see right here where it says stat diagnostics. It's naturally going to be off. You're going to turn that on. So mode, turn stat diagnostics on. So just go down here. See where that's highlighted? Make the blinking light go to on and hit enter. Now my diagnostics are on. Then we need to put the dots on our calculator. So we're going to go where? Second, y equal, and turn plots on. So second y equal, the plots are off. So I'm going to hit number 1 and then see how it's blinking on the on. I'm going to hit enter. So now my plots are on. Everybody there with me? Okay, now we need to put some data in. Where do we go to put data in? Stat, edit, and enter data. So we'll use this right here, right? We'll put those numbers in just so we have some of the same numbers. So stat, edit. Now go through and put those in. Aren't you glad you don't have to do these by hand? I had to do them by hand in college and I hated it. I actually like this now. Make sure they're all in there correct. And now you want to know, is this really linear, right? So stat, don't do anything yet, just go to stat calc. Now look at number 4 and number 8 and tell me what the difference is. What's the difference between choice number 4 and choice number 8? Yeah, one looks like algebra, One looks like statistics. Are you going to get the same answer either way? Let's do it both ways and see. So I'm going to go and do number 4. And then you just enter all the way through. And let's get our numbers. So I'm going to write those down. I'm going to go over here so I can see. I want to test this out. I don't believe my teacher. She lies. Just kidding. So if I were going to write this equation down, I would say y equals negative 115.115x plus 12.278, right? Let's go back to stat calc. You don't have to do anything with your numbers. They're all going to still the same number. So let's go to stat calc number 8. Go all the way through. And what does it say on top now? Now, A equals 12.278. B equals negative 0.115. R squared equals 0.755. R equals negative 0.869. Y equals 12.278 plus negative 0.115x. So, do you actually have, and you're getting all this out of the calculator, you didn't do any work. Does it matter which one you use? It's the same thing, right? If you're used to algebra and you like this one, I mean, it doesn't matter, right? AID is just going to kind of put it in the stat format. They like the y-intercept first. I don't know why. Right? Now, in order to graph that, I have 2 choices. I can either go to y equals and type in what I wrote down, or if I don't feel like doing any writing, I can go to y equals and I can do vars 5 equation, enter, and it will move it over there for me, right? So instead of me doing the work, I go to y equals and I say vars. I pick number 5, which is statistics. I tell it I want an equation, and they put it there for me. See, I don't have to type all the decimals in. It puts it there for me. If you go over, the advantage of this is you're a little bit more accurate because it pulls all those decimals. Okay? And now we're going to graph. Are you going to see anything when we graph? No. Why is nothing going to show up on your screen? Yeah, your screen is 10 by 10, and these are all bigger. So we do a zoom 9 or window, and you can adjust it by hand. Sometimes your calculator is not real friendly with how it makes your screen look, and you need to go play with the window yourself. Like if I'm looking at these, right, I'm going to want my x-axis to go all the way to 104, and I only need my y-axis to go to 12, right? But let's see what a zoom 9 will do. So now graph. Obviously, nothing shows, but while the little wheel is turning, okay, now I go zoom 9. Oh, there it is. I have my dots and my line going through them. The dots came from turning your plots on. The line came from going to y equals and getting that line over there. Does that make sense? What's different about this is you probably didn't know how to go to vars and bring that line over before. You had to type it in. We don't have to type it in now. If you do this, it eliminates the chance to make a mistake, right? Does it match your graph? Why, yes, it does, right? looks like what they had. So now let's see this, what we did so far is algebra. This right here is algebra. What's the slope? I'm going to put 3 decimals on these. They can get wrong pretty quick. So unless it tells you otherwise, keep 3 decimals. The y-intercept. R squared. Now this question right here that we just did is algebra. Oh, and the least squares regression line. Is this the same exact line? Yes, it's just a matter of what did you write first. So this little part was algebra. Now we're going to do statistics. These are the statistics style questions that would go with your old algebra. How is the slope interpreted? We don't just say the slope. We would say for every increase in degree, we predict there will be a decrease of 0.115 pounds of clothing. Do you all agree we dress differently when it's 20 degrees than if it's 105? Right? So again, we're interpreting more and not just writing answers down. What does R squared tells us? This is new for us. Not tells us. What R squared tells us is what percent we can explain. So that would mean 75.5% of observed values. What does observed mean? What are observed values? They're ones that you get, right? You didn't plug them in and predict them. We actually went out and measured pounds of clothing people were wearing. We actually got that data. So that's observed. We saw it versus predicted or calculated. That means we didn't see it, right? So 75.5% of observed values are explained by the straight line relationship. You could say linear relationship. So anytime you're asked this question, what does R squared mean? You repeat the same thing off. The only thing that really changes is that number, right? You get a different R squared. Now we can't keep going forever, right? Because there comes a point you got to wear something. So you can only get so light with your clothes. In the summer, you know, you're in your little tank top and shorts. Again, we can only extrapolate so far, right? Okay. How is the y-intercept interpreted? What does the y-intercept mean? What's the y-intercept? X is 0. So that's saying if it is 0 degrees, in this case, we're talking temperature, right? If it's 0 degrees, the pounds of clothing are, what was it? 12.278. This could matter if you're flying to Alaska, right? Because your bag gets weighed, true? You're going to have to wear that big heavy coat because you know it weighs a lot. So you'd be all like a marshmallow in the plane, right? So you don't have to pay to check it. Make a prediction. So if the temperature, somebody give us a prediction. Pick your favorite temperature. Blake, what's your favorite temperature?
72.
Okay. So if it's Blake's favorite temperature, which is 72, do I have to plug 72 in here to find the answer? Could I? I could. Do I have to? I don't. Because I can just go, right? I can go to my graph, my table. Now, it's a long way to 72. So I could type in second window and I could say 72. Go back to table. And how many pounds of clothing will I be wearing? 3.996. What did I say it would be? Or would be, I should say. We're predicting. What was it? 3.996? Does that make sense? So is this a interpolation or extrapolation? Now, wait a minute. Is 72 within here? Yes. So what would that be? Let's go back and look at that word so we know it. That would be what? Where did I write it? Oh, we would interpolate, right? Interpolate that information because it's within here. If I tried to predict clothing at 110 degrees, then that would be extrapolating because it's outside, right? Does that make sense? It's not hard. You've done it before in Algebra 2, but you didn't do this part, and you probably didn't talk about R squared at all. Figuring out what that means. Okay, so well, those are all the notes. Now we got to do some work.